What if I told you that right now, at this very moment, there's an object in space so deadly that a single teaspoon of it would weigh as much as Mount Everest? And if you could somehow bring that teaspoon to Earth, it would instantly drill through the planet's core like a cosmic bullet, emerging on the other side and continuing its journey through space. But here's what will blow your mind even more. These objects aren't rare cosmic curiosities. There are over 1 billion of them in our galaxy alone. They're called neutron stars, and they represent the most extreme physics laboratory in the universe. They're so dense that a sugar cube of neutron star material would weigh 100 million tons. They spin faster than your kitchen blender. Their magnetic fields are 1 trillion times stronger than Earth's, and they can kill you in ways that defy imagination. Think about this. The most dangerous thing you've probably worried about is maybe a nuclear bomb or a black hole you've seen in movies. But neutron stars? They make black holes look tame. They're stellar zombies, the collapsed cores of dead stars that refuse to die quietly. And the universe is absolutely crawling with them. Here's the revelation that changes everything. You are made of neutron star material. Every atom in your body, except hydrogen, was forged in the nuclear furnace of a massive star and scattered across space when that star exploded and left behind one of these cosmic monsters. You are literally made of stardust, and neutron stars are the cosmic foundries that made you possible. Before we dive into this mind-bending journey to the universe's most extreme objects, smash that like button if you're ready to have your understanding of reality completely transformed. Hit subscribe and ring the notification bell because we're about to explore physics so extreme it borders on science fiction. And I want to know, what country are you watching from? And what time is it where you are? Drop that in the comments because we're building a global community of cosmic explorers. And I love seeing how this incredible universe brings us all together across time zones and continents. Let's start with a question that will haunt you. What happens when the most fundamental forces of nature go to war with each other? For most of your life, you've lived in a universe governed by gentle forces. Gravity keeps you planted on Earth, but you can easily jump and temporarily defeat it. The electromagnetic force holds atoms together, but you can tear paper and break chemical bonds without thinking twice about it. The nuclear forces that hold atomic nuclei together seem impossibly distant from your daily experience. But neutron stars exist at the exact point where these forces engage in cosmic combat, and the results are so extreme they rewrite the rules of physics as you know them. Think of it like this. Imagine you're watching a boxing match between a featherweight and a heavyweight. For most of the universe's history, gravity is the featherweight, weak, easily overcome. But when a star runs out of fuel and begins to collapse, gravity suddenly becomes the ultimate heavyweight champion, and it starts winning fights it has no business winning. Here's what happens, and prepare to have your mind blown. When a star at least 8 times more massive than our sun reaches the end of its life, it faces an energy crisis. For millions of years, it's been fighting a constant battle, the outward pressure from nuclear fusion pushing against the inward pull of gravity. It's a perfect balance, like 2 wrestlers locked in an eternal stalemate. But then the fuel runs out. The nuclear furnace shuts down, and gravity wins in the most spectacular way possible. The star's core collapses in less than 1 second. Let me repeat that. In less time than it takes you to blink, an object larger than Earth crushes itself down to a sphere only about 12 miles across. The collapse is so violent, so catastrophic, that it creates pressures and temperatures that exceed anything else in the known universe, except for black holes and the first moments of the Big Bang itself. Now here's where it gets truly mind-bending. During this collapse, something happens that shouldn't be possible according to your everyday experience of matter. The electrons and atoms get crushed into the protons in the nucleus. They literally merge and become neutrons. Imagine if someone took your house and compressed it down to the size of a grain of sand, but somehow it still weighed exactly the same. That's essentially what happens to matter in a neutron star. But wait, there's more. Remember how I said these objects rewrite physics? Here's how. The matter in a neutron star becomes so dense that a cubic centimeter, about the size of a sugar cube, contains the same amount of matter as a mountain. We're talking about matter so compressed that the normal empty space in atoms completely disappears. To put this in perspective, think about your own body. You think you're solid, right? Wrong. You're mostly empty space. If you removed all the empty space between and within your atoms, your entire body would compress down to a particle smaller than a grain of dust. But you'd still weigh exactly the same. Now imagine that process happening to an entire star. That's a neutron star. And here's the detail that will keep you up at night. This isn't theoretical physics. We've detected over 3,000 of these objects. They're real. They're out there right now. And some of them are spinning 700 times per second while generating magnetic fields so powerful they could erase your credit cards from 100,000 miles away. The scientist who first predicted these cosmic impossibilities was Fritz Zwicky in 1934, just 1 year after the neutron itself was discovered by James Chadwick. Zwicky proposed that neutron stars would be so dense and so small that they would be essentially invisible. Most astronomers thought he was crazy. They weren't crazy enough. The reality turned out to be far more extreme than even Zwicky imagined. What happens next in our journey will challenge everything you thought you knew about the fundamental nature of matter, space, and time itself. Because we're about to discover that neutron stars don't just break the rules of physics. They reveal that the rules we thought we knew were just the beginning. What if I told you that the creation of a neutron star involves an explosion so powerful that for a brief moment, it outshines an entire galaxy containing 100 billion stars? We need to witness the most violent birth in the universe, a supernova explosion that creates these cosmic monsters. But here's the twist that will blow your mind. The explosion isn't what creates the neutron star. The neutron star creates the explosion. Let me take you inside a dying massive star and prepare yourself for a journey that defies everything your brain thinks it knows about cause and effect. Picture a star 20 times more massive than our sun. For 10 million years, it's been burning fuel in its core, fighting a constant battle against its own gravity. But unlike smaller stars that burn hydrogen steadily for billions of years, massive stars burn through their fuel like cosmic speed demons. Here's what happens in the final moments, and this timeline will haunt you. In the last year of its life, the star burns silicon in its core. In the last day, it's burning through nuclear fuel faster than you can imagine. In the last second before collapse, the core temperature reaches 100 billion degrees, 6,000 times hotter than the sun's core. And then, silence. The nuclear fusion stops, not gradually, not with warning. It just stops. What happens next occurs faster than your nervous system can process information. The core collapses from the size of Earth to the size of Manhattan in 15 milliseconds. That's 15 thousandths of a second. In that impossibly brief moment, the core becomes so dense that atomic nuclei touch each other directly, something that had never happened in the 13.8 billion year history of the universe, except perhaps in the first moments after the Big Bang. But here's where the physics becomes absolutely mind-bending. The collapse creates matter so dense that the normal forces that keep atomic nuclei apart simply surrender. Protons and electrons get crushed together to form neutrons. But it doesn't stop there. Think of it like this. Imagine you're bouncing a super ball against the floor. The harder you throw it down, the higher it bounces back up. The collapsing core of the star is like that super ball, but bouncing off a floor made of nuclear matter, so incompressibly dense that the bounce back sends a shockwave traveling outward at 30,000 kilometers per second. This shockwave rips through the outer layers of the star with such violence that it tears apart atomic nuclei and fuses them into heavier elements in real time. Every atom of gold in your jewelry, every atom of silver in your electronics, every atom of uranium used in nuclear power, all of it was created in the few seconds of a supernova explosion. But here's the detail that will give you chills. For about 10 seconds during this explosion, the newly formed neutron star releases more energy and neutrinos than our sun will produce in its entire 10 billion year lifetime. These ghost-like particles stream through space so densely that even though they barely interact with matter, trillions of them are passing through your body right now from supernovas that exploded thousands of years ago. The astronomer who first confirmed the existence of neutron stars was Jocelyn Bell Burnell in 1967. She was a graduate student at Cambridge University when she noticed strange, regular radio pulses coming from space. The signals were so regular, so precise, that her supervisor, Anthony Hewish, initially thought they might be communications from extraterrestrial intelligence. They nicknamed the source LGM-1 for Little Green Men. What they had actually discovered was a neutron star spinning 1.3 times per second, sweeping beams of radio waves across space like a cosmic lighthouse. They had found the first pulsar. But here's what will blow your mind about Bell Burnell's discovery. She almost didn't publish it. The signals were so strange, so unlike anything expected, that the scientific establishment nearly dismissed them as equipment malfunction or interference. It was only Bell Burnell's persistence and careful analysis that revealed the truth. And the truth was more bizarre than anyone had imagined. These weren't just spinning neutron stars. They were cosmic precision instruments. The pulsar Bell Burnell discovered keeps time more accurately than the most precise atomic clocks on Earth. Its period is stable to within 1 part in a billion. Think about what this means. Somewhere in space, there's an object made of matter so exotic that it shouldn't exist according to our everyday understanding of physics, spinning with such incredible precision that we can use it to navigate spacecraft and test Einstein's theories of relativity. But the birth of a neutron star creates something even more mind-bending than precise cosmic timekeepers. It creates objects so fundamentally weird that they challenge our basic understanding of what matter actually is. What we're about to explore next will make you question everything you thought you knew about the solid ground beneath your feet, because we're going to discover that matter itself might be just an illusion hiding something far more strange underneath. Here's a question that will restructure your understanding of reality. What happens when you compress matter beyond the point where atoms can exist? We're about to explore a realm of physics so extreme that it makes science fiction look conservative. Because inside a neutron star, matter exists in states that are so alien, so fundamentally different from anything you've ever encountered, that scientists are still arguing about whether we can even call it matter at all. Let's start with something that will blow your mind: the surface of a neutron star. You might think the surface would be hot gas, or maybe liquid metal like the core of the Earth. You'd be wrong in ways that defy imagination. The surface of a neutron star is solid, but it's not solid like anything you've ever touched. It's solid like a crystal lattice made of atomic nuclei, packed so tightly together that there's no room for electrons to orbit around them. The nuclei themselves form geometric patterns, hexagonal crystals of pure nuclear matter that extend for kilometers deep. Think of it like this. Imagine you took every car in a major city and somehow compressed them into a space the size of a parking spot, but they were still perfectly organized and structured. That's essentially what happens to atomic nuclei on a neutron star surface. But here's where it gets truly mind-bending. As you go deeper into a neutron star, the matter becomes increasingly exotic. About a kilometer down, the nuclei become so neutron-rich that they start forming shapes that don't exist anywhere else in the universe. Scientists call them nuclear pasta, and this isn't a joke name. At certain depths, the nuclei form long cylinders like spaghetti. Go deeper, and they form sheets like lasagna. deeper still, and they create tubes like rigatoni. These shapes emerge because the nuclear force is trying to minimize energy in an environment where matter is compressed beyond anything that existed in the early universe. Now prepare yourself for the truly impossible part, the core of a neutron star. Nobody knows what matter becomes under the extreme conditions at the center of a neutron star. The pressure is so intense, about 100 trillion times the pressure at the center of Earth, that neutrons themselves might break down into their constituent quarks and gluons. But here's what will keep you awake tonight. If quarks become unbound in the core of a neutron star, they might form something called strange matter. And strange matter has a property that sounds like something from a horror movie. It's contagious. Think about this carefully. If strange matter is more stable than normal matter, then any contact between strange matter and normal matter would convert the normal matter into strange matter. A single strange quark from a neutron star, if it somehow reached Earth, could theoretically convert our entire planet into a ball of strange matter in a matter of hours. This scenario, called a strangelet disaster, is so concerning that physicists had to carefully calculate whether high-energy particle experiments like the Large Hadron Collider could accidentally create stable strange matter. The good news? The calculations show it's impossible under terrestrial conditions. The bad news? We're still not entirely sure what's happening in the cores of neutron stars. But the weirdness doesn't stop with exotic matter. The gravitational field around a neutron star is so strong that it literally warps space and time in observable ways. Here's an experiment you can do with your imagination. Suppose you're standing on the surface of a neutron star. Ignore for a moment that you'd be instantly killed in about 12 different ways. If you held a ball at arm's length and dropped it, it would accelerate toward the surface at 200 billion meters per second squared. That's about 20 billion times stronger than Earth's gravity. But here's the detail that will blow your mind. The gravitational field is so strong that your head and your feet would experience significantly different gravitational pulls. The tidal forces would stretch your body like taffy before you even hit the surface. And time itself behaves strangely near a neutron star. Due to Einstein's general relativity, time runs slower in strong gravitational fields. On the surface of a neutron star, time would pass about 30% slower than it does on Earth. If you could somehow watch from a safe distance as someone fell onto a neutron star, you would see them appear to slow down and freeze just above the surface, their light becoming redder and dimmer until they faded from view. The physicist who first worked out the implications of neutron star matter was Robert Oppenheimer. Yes, the same Oppenheimer who led the Manhattan Project. In 1939, along with George Volkoff, he calculated the maximum possible mass of a neutron star. Above this limit, now called the Tolman-Oppenheimer-Volkoff limit, not even neutron degeneracy pressure can resist gravity's pull, and the object collapses into a black hole. But here's what makes Oppenheimer's calculations so remarkable. He was working with limited knowledge of nuclear physics, decades before we had any experimental data about neutron stars. Yet his calculations were accurate to within about 20% of modern values. He predicted that neutron stars could exist with masses between 0.1 and 3 solar masses, compressed into spheres only 10 to 15 kilometers in diameter. What Oppenheimer couldn't have predicted was that neutron stars would turn out to be even weirder than his equations suggested. Because neutron stars don't just sit quietly in space being impossibly dense. They spin, they pulse, they generate magnetic fields, and they do all of these things in ways that push physics to its absolute limits. What we're about to explore next will show you that neutron stars aren't just exotic objects. They're cosmic laboratories where the fundamental forces of nature engage in battles that determine the fate of matter itself. What if I told you that there are objects in space that keep better time than any clock ever built by humans, but they're also cosmic death machines that could sterilize entire planets. We need to talk about pulsars, neutron stars, that have become nature's most precise timepieces and most dangerous weapons rolled into one impossible package. And here's what will blow your mind. We've been using them to navigate through space and test the fundamental laws of physics, while completely underestimating just how lethal they really are. Let me paint you a picture that will haunt your dreams. Imagine a ball of matter 12 miles across, spinning 700 times per second with a magnetic field 1,000,000,000,000 times stronger than Earth's, shooting beams of radiation so intense they could kill you from 10,000 miles away. That's a pulsar, and there are thousands of them in our galaxy alone. But here's the detail that makes pulsars truly terrifying. They're not just spinning randomly. They're spinning with such incredible precision that they make atomic clocks look sloppy. The pulsar designated PSR 1937 plus 21 rotates 641 times per second. That's nearly the speed of sound at its equator. And it has maintained this rotation rate with such stability that if it were off by even a single rotation over the past 30 years, we would have noticed. Think of it like this. Imagine a figure skater pulling in their arms to spin faster, except the skater is made of nuclear matter, and they're spinning so fast that matter at their equator is traveling at nearly 25% the speed of light. The centrifugal force should tear the star apart. The fact that it doesn't tells us that neutron star matter is held together by forces we're only beginning to understand. Now here's where pulsars become truly mind-bending. They're cosmic particle accelerators that make our most advanced technology look like stone tools. The magnetic field around a pulsar is so intense that it literally tears electrons from atoms in the surrounding space and accelerates them to nearly the speed of light. These particles follow the magnetic field lines and get focused into narrow beams that shoot out from the pulsar's magnetic poles. But here's what will keep you up at night. These aren't gentle beams of light like a flashlight. A pulsar beam contains more energy than the combined electrical output of 1,000 nuclear power plants. When the beam sweeps across space, remember, the pulsar is spinning. It creates a lighthouse effect. But instead of warning ships away from danger, it's broadcasting death across interstellar space. If a pulsar beam were pointed directly at Earth from a distance of 1,000 light years, relatively close in cosmic terms, it would deliver a radiation dose that would kill every living thing on our planet's surface within hours. The atmosphere itself would be stripped away by the intense particle bombardment. And here's the terrifying part. We have no way of predicting when a pulsar might point its beam in our direction. As far as we know, we're constantly at the mercy of these cosmic death stars, and our continued existence depends on the random orientation of spinning neutron stars scattered throughout the galaxy. But the story of how we discovered pulsars reveals something fascinating about human nature and the process of scientific discovery. Remember Jocelyn Bell Burnell, who discovered the first pulsar in 1967. Here's what you probably don't know about that story, and it will make you angry. When Bell Burnell's discovery was announced, it was hailed as one of the most important astronomical discoveries of the 20th century. The Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars. But the prize went to her supervisor, Anthony Hewish, and to Martin Ryle for their contributions to radio astronomy. Bell Burnell, who actually made the discovery and fought to prove it wasn't equipment malfunction, was excluded from the award. This wasn't just an oversight. It reflected the systemic bias in science that consistently undervalued the contributions of women and graduate students. Bell Burnell herself has remained remarkably gracious about this injustice, but many scientists today consider it one of the most egregious snubs in Nobel Prize history. But here's what makes Bell Burnell's discovery even more remarkable. She almost didn't pursue the strange signals she was seeing. The pulses were so regular, so artificial seeming, that they initially seemed more likely to be human-made interference than astronomical phenomena. It was only her scientific curiosity and methodical approach that revealed the truth. And the truth was stranger than anyone had imagined. What Belle Burrell had found was proof that neutron stars existed. But more than that, she had discovered that these impossible objects could maintain rotational stability that exceeded human precision by orders of magnitude. Today, we use pulsars as cosmic GPS systems. The timing of pulsar signals is so precise that we can use them to detect gravitational waves, ripples in spacetime itself. When gravitational waves pass through the space between Earth and a pulsar, they slightly change the distance the pulsar signals have to travel, creating tiny timing variations that our most sensitive equipment can detect. This technique, called pulsar timing arrays, is how we confirmed the universe is filled with gravitational waves from merging supermassive black holes. We're literally using neutron stars as scientific instruments to study the most extreme phenomena in the cosmos. But here's the detail that will blow your mind. Pulsars are gradually slowing down as they emit energy. Over millions of years, their spin rate decreases, and eventually, they stop pulsing and become quiet neutron stars. But some pulsars, called millisecond pulsars, seem to have found a way to cheat death. These pulsars have been spun up by stealing matter from a companion star. As material spirals down onto the neutron star surface, it transfers angular momentum and causes the pulsar to spin faster, sometimes up to 700 times per second. These recycled pulsars can maintain their rapid rotation for billions of years. Think about what this means. There are neutron stars out there that have been spinning for longer than our solar system has existed, maintaining their rotation with precision that rivals our best atomic clocks, while generating magnetic fields that could erase every hard drive on Earth from millions of miles away. And we're just beginning to understand what they're capable of. What we're about to explore next will show you that when neutron stars interact with each other, they don't just create pretty light shows in space. They forge the very elements that make life possible, in explosions so violent they can be detected from across the observable universe. Here's a question that will redefine your understanding of cosmic violence. What happens when two objects, each containing the mass of the Sun, compressed into a sphere the size of a city, spiral into each other at half the speed of light? We're about to witness the most violent event in the universe since the Big Bang itself, a neutron star collision. And here's what will blow your mind. These catastrophic mergers don't just destroy everything in their vicinity, they create it. On August 17, 2017, humanity witnessed something that changed our understanding of the cosmos forever. For the first time in history, we detected gravitational waves, ripples in the fabric of spacetime itself, from two neutron stars spiraling into each other in a galaxy 130 million light-years away. But here's the detail that will haunt you. This collision didn't just happen on August 17, 2017. It happened 130 million years ago, when the most complex life on Earth was barely multicellular. The gravitational waves, traveling at the speed of light, had been racing toward us across the universe for longer than complex life has existed on our planet. And when those waves finally reached us, they revealed something that will restructure your understanding of existence itself. Let me take you through what happens during a neutron star merger, and prepare yourself for physics so extreme it borders on cosmic horror. Two neutron stars, each about 1.4 times the mass of the Sun, are locked in a death spiral. They're orbiting each other at increasingly rapid speeds as they lose energy by radiating gravitational waves. Think of it like two massive bowling balls rolling around the curved surface of a trampoline, except the trampoline is spacetime itself, and the bowling balls are made of matter so dense that a teaspoon would weigh as much as a mountain. In the final moments before collision, these neutron stars are orbiting each other 1,000 times per second. The orbital speed reaches 100,000 kilometers per second, 1/3 the speed of light. The gravitational forces involved are so extreme that they literally deform the neutron stars, stretching them into egg shapes before they merge. Now here's where it gets truly mind-bending. The collision itself lasts only milliseconds, but in those brief moments, it recreates conditions that haven't existed since the first seconds after the Big Bang. When the neutron stars finally touch, the collision produces temperatures of 100 billion degrees. Matter gets compressed to densities that might exceed even those found in neutron star cores. And in this cosmic furnace, nuclear alchemy takes place on a scale that dwarfs anything else in the modern universe. Here's what will blow your mind. Every atom of gold in your wedding ring, every atom of platinum in your car's catalytic converter, every atom of uranium in nuclear fuel, all of it was created in neutron star mergers. Not in the cores of massive stars, not in supernovas, but in these incredibly rare collisions between the universe's most extreme objects. The process is called R-process nucleosynthesis, rapid neutron capture, and it only happens under the most extreme conditions imaginable. During a neutron star merger, atomic nuclei are bombarded with so many neutrons so quickly that they can capture neutrons faster than they can decay. This creates incredibly neutron-rich isotopes that rapidly decay into the heavy elements that make modern technology possible. Think about this. The smartphone in your pocket contains elements that were created in explosions so violent they temporarily outshone entire galaxies. The rare earth elements that make your computer screen work, the gold in your electronics, the silver in your jewelry, all of it is quite literally made from cosmic catastrophe. But the 2017 collision, designated GW170817, revealed something even more profound. For the first time, we detected both gravitational waves and electromagnetic radiation from the same cosmic event. This opened an entirely new field of astronomy called multi-messenger astrophysics. Here's what happened. When the LIGO detectors in the United States and the Virgo detector in Italy detected gravitational waves from the collision, they immediately sent alerts to observatories around the world. Within hours, telescopes in space and on Earth were pointed at the source, and what they saw was unprecedented. The collision produced what's called a kilonova, an explosion that's 1,000 times brighter than a regular nova. The light curve, how the brightness changed over time, matched theoretical predictions. For our process nucleosynthesis almost perfectly. Scientists could literally watch heavy elements being created in real time. But here's the detail that will give you chills. The gravitational waves from this collision were so precisely measured that we could determine the collision happened 130 million years ago, plus or minus just a few days. We could see the aftermath of an explosion that occurred when dinosaurs ruled the Earth. With precision, it would have been impossible just a decade earlier. The scientists who made this detection possible include Kip Thorne, Rainer Weiss, and Barry Barish, who won the 2017 Nobel Prize in Physics for their work on LEGO. But what's remarkable is that they spent decades developing the technology to detect gravitational waves, waves so subtle that they change the length of LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. Think about what that means. We built machines so sensitive they can detect changes smaller than the nucleus of an atom, across distances of several kilometers, and we use them to observe collisions that happened before complex life existed on Earth. And here's what will keep you up at night. Neutron star mergers like GW170817 happen roughly once every 100,000 years in a galaxy like ours. That might sound rare, but consider this. There are over 100 billion galaxies in the observable universe, which means that right now, somewhere in space, neutron stars are colliding and creating the elements that make life possible. But neutron star collisions don't just create elements. They might also create something far more exotic and potentially dangerous. Some theoretical models suggest that neutron star mergers could produce black holes, but not just any black holes. They might create rapidly spinning black holes surrounded by accretion disks of exotic matter. And these systems could become something called gamma-ray bursts, the most energetic explosions in the known universe. A gamma-ray burst pointed directly at Earth from within our own galaxy would be an extinction-level event. The radiation would strip away our ozone layer and trigger a global ice age that could end most life on our planet. But here's the twist that makes this even more concerning. We have no way to predict when or where these collisions will happen. We're essentially living in a cosmic shooting gallery, where the bullets are made of collapsed stellar cores, and the guns fire randomly across billions of years. What we're about to explore next will show you that the dangers posed by individual neutron stars pale in comparison to what happens when these objects become part of larger cosmic systems. Because we're about to discover that neutron stars can become components in structures so massive and so energetic that they challenge our understanding of what's possible in this universe. What if I told you that there are neutron stars so magnetically powerful that they could kill you by restructuring the atoms in your body from a distance of 600 miles? We need to talk about magnetars, neutron stars with magnetic fields so intense they break the laws of physics as we normally understand them. And here's what will blow your mind. These cosmic monsters don't just passively threaten everything around them. They actively hunt. In December 2004, something happened that forced astronomers to rewrite their understanding of neutron stars. A burst of gamma rays hit Earth's atmosphere with such intensity that it temporarily blinded every X-ray satellite in space and disrupted radio communications around the globe. The source? A magnetar located 50,000 light-years away in the constellation Sagittarius. Think about that distance. This object was halfway across our galaxy, and it still delivered enough energy to affect Earth's magnetosphere and upper atmosphere. If that same magnetar had been located 10 light-years away, still incredibly distant by human standards, it would have caused a mass extinction event that would have made the asteroid that killed the dinosaurs look like a minor inconvenience. But here's what makes magnetars truly terrifying. Their magnetic fields are so strong that they violate what physicists call the Schwinger limit, the theoretical maximum magnetic field strength beyond which empty space itself begins to break down and create matter from nothing. Let me put this in perspective with an analogy that will haunt your dreams. Imagine you have a magnet so powerful that it doesn't just attract metal objects. It actually creates metal objects from thin air. That's essentially what happens around a magnetar. The magnetic field is so intense that it literally pulls electron-positron pairs out of empty space. The magnetic field strength around a magnetar reaches 100 billion Tesla. To understand how impossibly strong this is, consider that the strongest magnetic field ever created by humans in a laboratory was about 1,200 Tesla, and it existed for only a fraction of a second before destroying the equipment that created it. The magnetic field around a magnetar is 100 million times stronger than that, and it maintains this intensity for millions of years. Here's what will blow your mind about these magnetic fields. They're so powerful that they affect matter at the subatomic level. In a magnetar's magnetic field, atoms become elongated into needle-like shapes. The electron orbits that normally form spherical shells around atomic nuclei get compressed into thin pancakes. Matter literally changes its fundamental structure. But the truly terrifying part is what happens when magnetars become active. Most of the time, magnetars are relatively quiet, just sitting in space with their incomprehensibly strong magnetic fields. But occasionally, something triggers what's called a starquake. Think of it like this. The crust of a magnetar is made of crystallized atomic nuclei under such intense magnetic stress that it's like a spring compressed to its breaking point. When the magnetic field lines suddenly rearrange themselves, a process that's still not fully understood, the crust literally cracks like the shell of an egg. But this isn't a gentle crack. The energy released in a magnetar starquake is equivalent to all the energy our sun will produce over 200,000 years, released in a matter of seconds. And this energy gets converted into the most dangerous form of electromagnetic radiation possible, gamma rays. The magnetar SGR 1806-20 experienced such a starquake in 2004. Located 50,000 light-years from Earth, this event was detected by spacecraft throughout the solar system. The gamma-ray burst was so intense that it actually changed the ionization level of Earth's upper atmosphere during daylight hours, something that had never been observed before from such a distant source. Here's the detail that will keep you awake. If SGR 180620 had been located just 10 light-years from Earth, the gamma-ray burst would have delivered a radiation dose equivalent to being 30 feet away from a nuclear bomb explosion. Every living thing on the side of Earth facing the magnetar would have been killed instantly, and the ozone depletion would have triggered a global ecological collapse. And we have no way to predict when these starquakes will happen. Magnetars can remain quiet for decades, and suddenly release more energy in 10 seconds than the sun produces in 200 millennia. But here's what makes magnetars even more mysterious. We don't fully understand how they form. The leading theory is that they're created when the most massive stars, at least 40 times more massive than the sun, undergo core collapse, but with an unusual twist. Instead of forming a regular neutron star, the collapse somehow amplifies and traps the original star's magnetic field, concentrating it by a factor of trillions. The physicist who first proposed the existence of magnetars was Robert Duncan of the University of Texas, working with Christopher Thompson of the Canadian Institute for Theoretical Astrophysics. In 1992, a theoretical work predicted that neutron stars could have magnetic fields up to 1,000 times stronger than typical pulsars. But even Duncan and Thompson underestimated how extreme these objects could be. When the first magnetar was confirmed in 199 SGR 052666, its magnetic field was measured at nearly 100 times stronger than their most optimistic predictions. Here's what will blow your mind about magnetars. They're cosmic time bombs with unpredictable fuses. We've identified about 30 confirmed magnetars in our galaxy, but theoretical models suggest there could be tens of thousands of them scattered throughout the Milky Way. Most of them are probably dormant, appearing as ordinary neutron stars until something triggers a starquake. And when they do become active, they don't just affect their immediate surroundings. The most powerful magnetar flares can disrupt satellite communications, GPS systems, and even power grids on Earth from thousands of light years away. We're essentially living in a galaxy filled with cosmic weapons that could cripple our technological civilization without warning. But perhaps the most unsettling thing about magnetars is what they reveal about the nature of magnetic fields themselves. In everyday experience, magnetic fields seem gentle, almost playful. You can wave a magnet around, stick it to your refrigerator, use it to pick up paper clips. But magnetars show us that magnetic fields can become forces of cosmic destruction. They can restructure matter, create particles from empty space, and release energy that outshines entire galaxies. They remind us that the gentle forces we experience in daily life are just the tip of an iceberg that extends down into realms of physics so extreme they border on the impossible. What we're about to explore next will take us even deeper into the alien physics of neutron stars, because we're going to discover that these objects don't just exist in isolation. They can form binary systems with other exotic objects, creating cosmic laboratories where Einstein's most mind-bending predictions about spacetime play out in real time. Here's a question that will redefine your understanding of spacetime itself. What happens when two neutron stars become locked in an orbital dance that's slowly destroying the fabric of the universe around them? We're about to explore binary neutron star systems, cosmic laboratories where Einstein's most abstract theories become visible reality, where the curvature of spacetime itself becomes a source of energy that can be detected from billions of light years away. But here's what will blow your mind. These systems aren't just producing gravitational waves. They're losing energy by radiating gravitational waves. And that energy loss is causing them to spiral inward toward an inevitable collision that will reshape our understanding of cosmic evolution. Let me tell you about PSR 1913+16, discovered in 1974 by Russell Hulse and Joseph Taylor. This system consists of two neutron stars orbiting each other every 7.75 hours. But here's the detail that earned Hulse and Taylor the Nobel Prize. The orbital period is decreasing by exactly the amount predicted by Einstein's general theory of relativity. Think about what this means. Einstein's equations predicted that two massive objects orbiting each other would lose energy by creating ripples in spacetime, gravitational waves. But in 1974, we had no direct way to detect these waves. PSR 1913+16 became the first indirect proof that gravitational waves exist, because the orbital decay matched Einstein's predictions to within 0.2%. For over 40 years, astronomers have been monitoring this system, and the agreement with Einstein's theory has only gotten better. The orbital decay has proceeded exactly as predicted, confirming one of the most exotic predictions of general relativity with precision that exceeds most laboratory experiments. But here's what will keep you up at night. PSR 1913+16 is doomed. The two neutron stars are spiraling inward, and in about 300 million years, they will collide in an explosion that will be visible from across the observable universe. And that collision is just one of thousands happening throughout the cosmos right now. The 2015 detection of gravitational waves by LIGO opened an entirely new window into the universe. And what we've seen through that window is both beautiful and terrifying. We've detected dozens of gravitational wave events, black hole mergers, neutron star mergers, and exotic combinations that challenge our understanding of stellar evolution. But here's the detail that will blow your mind. Every gravitational wave detection tells us a story about cosmic catastrophe. Each signal represents the final moments of objects so massive and so compact that their death throws send ripples through the fabric of space-time itself. The LIGO detectors work by measuring incredibly tiny changes in the length of laser beams traveling down 4-kilometer-long arms. When a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. The change in length is so small that it defies human intuition, less than 1/10,000th the width of a proton. To put this in perspective, imagine you're trying to measure the distance from Earth to the nearest star, and you want to detect a change in that distance equal to the width of a human hair. That's roughly equivalent to the sensitivity required for gravitational wave detection. Yet this seemingly impossible measurement has revolutionized our understanding of the universe in just a few short years. Here's what gravitational wave astronomy has revealed. The universe is far more violent than we ever imagined. Black holes merge regularly. Neutron stars collide and create kilonovas. And these events are happening constantly, all around us, at rates that suggest our cosmic neighborhood is far more dynamic and dangerous than we previously understood. But binary neutron star systems aren't just cosmic time bombs. They're also precision instruments that allow us to test the fundamental laws of physics under conditions that can't be replicated in any laboratory. The neutron stars in PSR 1913+16 have masses of 1.44 and 1.39 solar masses, compressed into spheres only about 20 kilometers in diameter. Their orbital velocities reach a significant fraction of the speed of light. The gravitational fields are so strong that they cause measurable time dilation and redshift effects. By studying these systems, we can test Einstein's theory of general relativity in the strong field regime, conditions where gravity is so intense that it dominates all other forces. And every test has confirmed Einstein's predictions with stunning accuracy. But here's where it gets truly mind-bending. Some binary systems contain neutron stars paired with other exotic objects. PSRJ 07373-039 is a system containing two pulsars, two neutron stars that we can observe directly because they both sweep radio beams across Earth as they spin. This system is the ultimate laboratory for testing general relativity. We can measure not just the orbital decay due to gravitational wave emission, but also exotic effects like the precession of the orbital ellipse, gravitational redshift, and even the way the pulsar's radio beams are bent by their companion's gravitational field. And every measurement confirms that space-time really is curved, that massive objects really do create distortions in the fabric of reality, and that these distortions propagate outward at the speed of light as gravitational waves. Think about what this means for your understanding of reality. Space and time aren't fixed, unchanging backdrops against which events occur. They're dynamic, malleable aspects of reality that can be stretched, compressed, and rippled by the motion of massive objects. Right now, as you're reading this, gravitational waves from dozens of binary systems throughout the galaxy are passing through your body. These waves are so weak by the time they reach Earth that they don't affect you in any measurable way. But they're there, invisible ripples in space-time itself, carrying information about cosmic catastrophes that happened millions of years ago. But here's the detail that will give you chills. Some theoretical models predict that binary neutron star systems could create closed time-like curves, regions of space-time, where cause and effect become scrambled, where it might theoretically be possible to travel backward in time. These exotic space-time geometries, if they exist, would only occur in the immediate vicinity of merging neutron stars, under conditions so extreme that no material object could survive to take advantage of them. But the fact that Einstein's equations allow for such possibilities shows just how alien the physics around neutron stars really is. What we're about to explore next will show you that neutron stars don't just warp space-time. They can become components in cosmic structures so energetic and so massive that they challenge our understanding of what's possible in this universe. What if I told you that neutron stars can become parts of cosmic monsters, so powerful they can accelerate particles, to energies that make our most advanced particle accelerators look like children's toys? We're about to explore neutron stars in the most extreme environments the universe has to offer, systems where these already impossible objects become components in cosmic machines that generate energies and create phenomena that push the boundaries of known physics. Let's start with something that will redefine your understanding of cosmic violence: neutron stars that fall into black holes. In 2020, the LIGO-Virgo collaboration detected gravitational waves from an event designated GW200105 and GW20115, the first confirmed detections of neutron stars being torn apart and devoured by black holes. But these weren't gentle, gradual processes. They were cosmic feeding frenzies that released more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. Here's what happens when a neutron star approaches a black hole, and prepare yourself for physics that borders on cosmic horror. As the neutron star spirals inward, the black hole's gravity begins to deform it. The side closest to the black hole experiences stronger gravitational pull than the far side, tidal forces that would stretch a human body like taffy. But neutron stars are held together by nuclear forces so strong they can initially resist even black hole tides. For a brief moment, the neutron star maintains its integrity as it orbits at a significant fraction of light speed just outside the black hole's event horizon. Then suddenly, catastrophically, the tidal forces win. The neutron star gets torn apart in a process called spaghettification, stretched into a long, thin stream of nuclear matter that spirals into the black hole like water going down a cosmic drain. But this isn't ordinary matter. This is material so dense that a handful would weigh as much as a mountain, being accelerated to nearly light speed and heated to temperatures of billions of degrees. The collision produces a kilonova explosion, similar to neutron star mergers, but with a twist that makes it even more exotic. The black hole's intense gravitational field affects how the heavy elements created in the explosion are distributed through space, potentially creating pockets of space enriched with rare isotopes that don't exist anywhere else in the universe. But here's what will blow your mind. We detected the gravitational waves from these events using instruments on Earth, 900 million light years away. We literally felt the space-time ripples created by neutron stars being devoured by black holes in distant galaxies. Think about what that means. The universe is so violent, these catastrophic events so energetic, that their effects propagate across nearly 1 billion light years of space and still register on our detectors as measurable distortions in the fabric of reality itself. But neutron star-black hole mergers pale in comparison to what happens when neutron stars become involved with the most energetic phenomena in the known universe: gamma-ray bursts. Gamma-ray bursts are the brightest electromagnetic events known to occur in the universe. For a few seconds to a few minutes, a gamma-ray burst can outshine all the stars in its host galaxy combined. The energy released is so enormous that it challenges our understanding of what's physically possible. And neutron stars, specifically, highly magnetized neutron stars called magnetars, are likely the engines that power at least some of these cosmic catastrophes. Here's the theory that will keep you awake at night. When certain massive stars collapse, they don't form regular neutron stars. Instead, they form magnetars with magnetic fields so intense that they can focus the star's collapse energy into narrow jets that shoot out along the magnetic poles at nearly the speed of light. These jets contain matter accelerated to such high energies that when they interact with the surrounding interstellar medium, they produce gamma rays with energies that exceed anything we can create in particle accelerators by factors of millions. But here's the truly terrifying part. If one of these gamma-ray bursts were pointed directly at Earth from within our own galaxy, it would be an extinction-level event. The gamma radiation would destroy our ozone layer, trigger global climate change, and potentially end most complex life on our planet. The astronomer who first proposed that gamma-ray bursts might be powered by neutron stars was Stan Woosley of UC Santa Cruz in the 1990s. Collapser Rodel suggested that certain types of stellar collapse could create rapidly spinning neutron stars or black holes surrounded by accretion disks, and that the interaction between the collapsed object's magnetic field and the eye disk could focus energy into relativistic jets. What makes Woosley's model remarkable is that it predicted many of the properties of gamma-ray bursts that were later confirmed by observation: their duration, their energy distribution, and their association with certain types of supernovas. But the reality turned out to be even more extreme than Woosley predicted. Some gamma-ray bursts release more energy in 10 seconds than our sun will produce over its entire lifetime. The most energetic gamma-ray burst ever detected, GRB 221009A, detected in October 2022, was so bright that it temporarily blinded gamma-ray detectors in space and was visible to amateur radio astronomers on Earth, despite being located 2.4 billion light-years away. Think about that. An explosion that happened when the most complex life on Earth, with single-celled organisms, was still bright enough 2.4 billion years later to interfere with satellites in orbit around our planet. But neutron stars don't just participate in these extreme events. They can also be created by them. When gamma-ray bursts are produced by collapsing massive stars, the end result is often a rapidly spinning neutron star with properties that are barely within the realm of theoretical possibility. These millisecond magnetars can spin hundreds of times per second while maintaining magnetic fields quadrillions of times stronger than Earth's. They exist at the very edge of what neutron star physics allows: any faster rotation or stronger magnetic field, and they would literally fly apart or collapse into black holes. And here's the detail that will blow your mind. Some theoretical models suggest that these extreme neutron stars might be able to create magnetic reconnection events so powerful that they could accelerate particles to energies that approach the theoretical maximum possible in our universe, the GZK cutoff energy, where particles become so energetic that they interact with cosmic microwave background radiation. If these models are correct, neutron stars might be the source of the most energetic particles ever detected. Cosmic rays with energies that exceed anything we can produce in terrestrial accelerators by factors of 100 million. But perhaps the most mind-bending possibility is that neutron stars in extreme environments might create conditions where the fundamental constants of physics themselves become variable. In the intense gravitational and magnetic fields around neutron stars, some theories predict that the fine structure constant, which determines the strength of electromagnetic interactions, might actually change value. If this is true, then neutron stars aren't just laboratories for extreme physics. They're regions where physics itself becomes fundamentally different from what we experience on Earth. What we're about to explore next will show you that despite all these cosmic extremes, neutron stars might actually be connected to the most intimate aspects of your existence, because they might be the cosmic factories that created the very conditions necessary for life to emerge in the universe. Here's a question that will fundamentally change how you see your place in the cosmos. What if I told you that neutron stars aren't just exotic objects in distant space, but the cosmic architects that built the very foundation of reality as you know it? We're about to explore the deepest connection between you and the universe's most extreme objects, a connection so profound that it will make you see every element in your body, every planet in the solar system, and every condition that makes life possible as direct products of neutron star catastrophes. But first, let me blow your mind with a revelation that challenges everything you thought you knew about the origin of heavy elements. For decades, astronomers believed that most elements heavier than iron were created in the cores of massive stars during supernova explosions. This seemed to make sense. Supernovas are incredibly energetic. They scatter material across space, and they happen frequently enough to explain the abundance of heavy elements we observe in the universe. They were wrong. Catastrophically, beautifully wrong. The 2017 detection of the neutron star merger, GW170817, didn't just confirm that these collisions produce gravitational waves. It revolutionized our understanding of cosmic chemistry. The kilonova explosion that followed the merger produced a light curve that perfectly matched theoretical predictions for our process nucleosynthesis. But here's what will keep you up at night. The amount of gold created in that single collision was equivalent to several times the mass of Earth. Think about that. One collision between two neutron stars, lasting only seconds, produced more gold than exists in our entire planet. But it gets more mind-bending. Follow-up observations of the merger site showed that the explosion created not just gold, but platinum, uranium, rare earth elements, and isotopes that are crucial for everything from medical imaging to nuclear power to the semiconductors in your phone. Here's the revelation that changes everything. Nearly every atom in your body, heavier than iron, was forged in the cosmic furnace of a neutron star collision. The iron in your blood, the calcium in your bones, the zinc that's essential for your immune system. All of it was created when neutron stars tore each other apart in explosions, so violent they temporarily outshone entire galaxies. But the connection goes deeper than just elemental composition. The timing of neutron star mergers throughout cosmic history has directly influenced the evolution of life in the universe. In the early universe, heavy elements were incredibly rare. The first stars contained almost no elements heavier than lithium. They were made almost entirely of hydrogen and helium. But as neutron star mergers scattered heavy elements through space, subsequent generations of stars incorporated these elements into their composition. And here's where it gets personal. The formation of planets like Earth depends on having enough heavy elements to create rocky worlds with solid surfaces and complex chemistry. Without neutron star mergers enriching the galaxy with heavy elements over billions of years, planetary systems like ours couldn't exist. The astronomer who first calculated the cosmic importance of neutron star mergers for heavy element production was Anna Frebel of MIT. Her work on ancient stars, some of the oldest objects in our galaxy, revealed that their heavy element compositions could only be explained by our process nucleosynthesis in neutron star mergers. But Frebel's research revealed something even more profound. The pattern of heavy elements in ancient stars suggests that neutron star mergers were more frequent in the early universe than they are today. This means that the cosmic conditions that made Earth-like planets possible were established by a period of intense neutron star collisions billions of years ago. Think about what this means for your existence. You are not just made of stardust, you are made of neutron star merger debris. Every complex molecule in your body owes its existence to cosmic catastrophes, so violent they shake the fabric of spacetime itself. But the influence of neutron stars on the conditions for life goes beyond just creating heavy elements. The magnetic fields around neutron stars might have played a crucial role in organizing the structure of galaxies and triggering star formation in specific regions. When neutron stars are created in supernova explosions, they're often ejected from their birthplaces at high speeds, sometimes exceeding 1,000 kilometers per second. These runaway neutron stars travel through the galaxy, and their powerful magnetic fields can trigger the collapse of gas clouds and initiate new rounds of star formation. Some theoretical models suggest that the pattern of star formation in the Milky Way, including the formation of our solar system, has been influenced by the paths of runaway neutron stars through the galactic disk. If this is true, then neutron stars haven't just provided the raw materials for planets. They've also helped orchestrate the cosmic conditions that led to the formation of the solar system itself. But here's where the connection becomes truly mind-bending. Neutron stars might have influenced the evolution of life on Earth in ways that are only now being understood. High-energy cosmic rays, many of which may originate from neutron star environments, constantly bombard Earth's atmosphere and surface. These cosmic rays can cause mutations in DNA, and some scientists have proposed that cosmic ray-induced mutations have been a driving force in biological evolution. If neutron stars are major sources of high-energy cosmic rays, then these objects haven't just created the chemical elements that make life possible, they've also provided one of the mechanisms that drives evolutionary change. Think about the implications. The same objects that forged the atoms in your body might also have contributed to the genetic mutations that led to the evolution of complex life, including ultimately the development of human intelligence that allows you to contemplate your cosmic origins. But perhaps the most profound connection between neutron stars and life is temporal. Neutron stars are incredibly long-lived objects. Once formed, they can exist for trillions of years, far longer than the current age of the universe. This means that neutron stars created in the early universe are still out there, still influencing cosmic evolution, still participating in the ongoing story of how the universe creates conditions suitable for life. And here's the detail that will give you existential chills. Some of the neutron stars that contributed to the heavy element enrichment that made Earth possible might still be detectable today as pulsars or magnetars. When you look up at the night sky, some of those faint radio sources that require telescopes to detect might be the very objects that created the calcium in your bones and the iron in your blood. You are not separate from the cosmos. You are a direct product of its most extreme processes. The neutron stars scattered throughout the galaxy aren't alien objects existing in a realm disconnected from your experience. They are your cosmic ancestors, the foundries that created the raw materials from which you are built. But this connection raises a question that will challenge your understanding of consciousness itself. If you are made of neutron star merger debris, and if neutron stars represent matter in its most exotic possible state, what does that say about the nature of your own existence? We're about to explore this question and discover that the physics of neutron stars might provide unexpected insights into the deepest mysteries of consciousness, free will, and the nature of information itself. Here's a question that will shatter your understanding of what information actually is. What happens to the information encoded in the quantum states of matter when that matter gets compressed beyond the point where atoms can exist? We're about to explore one of the deepest mysteries in modern physics, the information paradox as it relates to neutron stars. And here's what will blow your mind. The answer to this question doesn't just tell us about exotic objects in space. It reveals fundamental truths about the nature of reality, consciousness, and the very fabric of existence itself. Let me start with a concept that will restructure your thinking. Information is physical. This isn't just a philosophical statement. It's a fundamental principle of physics, discovered by researchers like John Wheeler, and later developed by physicists like Leonard Susskind and Gerard T. Hooft. Every particle, every atom, every molecule in your body contains information. Quantum information that describes its precise state, its history, its relationships with other particles. This information isn't just data about the particle. According to quantum mechanics, it literally is the particle in the most fundamental sense. Now here's where neutron stars create a mind-bending paradox. When matter collapses to form a neutron star, what happens to all the information that was encoded in the original atomic structure? Think about this carefully. A neutron star contains roughly 1 to 2 solar masses worth of matter compressed into a sphere 20 kilometers across. That matter originally existed as perhaps 1,057 individual atoms, each with its own quantum state, its own information content. But in a neutron star, those atoms have been crushed out of existence, their electrons forced to merge with protons to create neutrons. The question that will keep you up at night is this: where did all that quantum information go? According to the fundamental principles of quantum mechanics, information cannot be destroyed. This principle, called quantum information conservation, is as fundamental to physics as the conservation of energy. Yet neutron star formation appears to violate this principle on a massive scale. Here's where it gets even more mind-bending. Some theoretical physicists, including Nobel laureate Gerard T. Hooft, have proposed that all the information about a neutron star's interior might actually be encoded on its surface, a concept called the holographic principle. Think of it like this. Imagine you have a hologram, a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests that all the information about what's happening inside us neutron star might be encoded in quantum fluctuations on its two-dimensional surface. If this is true, then neutron stars aren't just exotic forms of matter. They're cosmic information storage devices that preserve the quantum states of all the matter that collapsed to form them. But here's the detail that will blow your mind. If the holographic principle applies to neutron stars, it might also apply to the universe as a whole. Some cosmologists have proposed that all the information about our three-dimensional reality might actually be encoded on a two-dimensional surface at the edge of the observable universe. This would mean that everything you think of as real, your body, Earth, the solar system, the galaxy, might actually be projections from information encoded on a distant cosmic surface. You might literally be living inside a hologram. The physicist who first applied the holographic principle to neutron stars was Juan Maldacena of the Institute for Advanced Study at Princeton. His work showed that certain types of gravitational systems could be mathematically equivalent to quantum field theories, operating on their boundaries. But Maldacena's work revealed something even more profound. The relationship between gravity and quantum mechanics might be fundamentally holographic. This suggests that our three-dimensional experience of reality might emerge from more fundamental two-dimensional information processing, occurring at boundaries we can't directly observe. Now here's where this connects to consciousness in ways that will challenge everything you believe about your own existence. Some researchers have proposed that consciousness itself might be a holographic phenomena. Think about how your brain works. You have roughly 86 billion neurons, each connected to thousands of others through synapses. The information processing that creates your thoughts, memories, and sense of self emerges from the complex interactions between these neurons. But here's the mind-bending possibility. Some neuroscientists and physicists have suggested that consciousness might not actually reside in the three-dimensional structure of your brain. Instead, it might emerge from information processing occurring on two-dimensional surfaces, possibly the boundary layers between different regions of neural tissue. If consciousness is holographic, then your sense of self, your thoughts, your memories, your experience of being a unified individual might actually be a projection from quantum information processing occurring on surfaces within your brain that you're not directly aware of. And here's where neutron stars become relevant to consciousness. If these cosmic objects can preserve vast amounts of quantum information in holographic form, they demonstrate that the universe has mechanisms for maintaining information even under the most extreme conditions imaginable. This raises a possibility that borders on science fiction, but is grounded in serious physics. Could consciousness, as an information pattern, survive the death of the brain that created it? Some physicists, including Sir Roger Penrose and Stuart Hameroff, have proposed that consciousness might be based on quantum information processing that could, in principle, persist beyond biological death. If quantum information about conscious states could be preserved in the same way that neutron stars preserve information about collapsed matter, then some form of consciousness might survive the destruction of its original physical substrate. But let's bring this back to something more immediate and verifiable. What neutron stars reveal about the nature of information in our universe. The study of neutron star physics has led to the development of new mathematical tools for understanding how information behaves under extreme conditions. These tools have applications far beyond astrophysics. They're being used to develop quantum computers, to understand black hole physics, and to explore the fundamental nature of spacetime itself. Here's what will blow your mind. Some of the algorithms being developed for quantum computing are directly based on mathematical techniques originally developed to understand neutron star structure. The same equations that describe how matter behaves under extreme density and pressure are now being used to process information in quantum computers. This means that neutron stars aren't just exotic objects to observe and study. They're cosmic laboratories that reveal fundamental principles about how information can be processed and preserved under extreme conditions. These principles are now being applied to develop technologies that could revolutionize computing, communication, and our understanding of consciousness itself. But perhaps the most profound implication is what neutron stars suggest about the persistence of information in the universe. If quantum information really cannot be destroyed, and if neutron stars demonstrate mechanisms for preserving information under extreme conditions, then everything that has ever happened in the universe, every thought, every experience, every moment of consciousness, might still exist somewhere in the quantum structure of reality. You might not just be made of neutron star merger debris. You might also be part of a cosmic information processing system that preserves and processes the quantum history of everything that has ever existed in the universe. What we're about to explore next will show you how this cosmic perspective on information and consciousness connects to the most personal aspects of your existence, and how understanding neutron stars can actually change how you experience your daily life. Here's a question that will transform how you experience every moment of your existence. What does it mean to live your daily life knowing that you are quite literally made of cosmic catastrophe, animated by information patterns that might persist beyond the death of stars themselves? We're about to explore how understanding neutron stars doesn't just change your knowledge of astronomy. It fundamentally alters your relationship with reality, your sense of purpose, and your understanding of what it means to be conscious in this universe. Let's start with something immediate and tangible. every breath you take. Right now, as you breathe, you're inhaling oxygen atoms that were forged in the nuclear cores of massive stars and scattered across space when those stars exploded and left behind neutron stars. The iron in your blood that carries that oxygen throughout your body was created in supernova explosions that created neutron stars. The calcium in your bones, the phosphorus in your DNA, the trace metals that are essential for your neural function, all of it was created in cosmic events so violent they temporarily outshone entire galaxies. But here's what makes this personal. You're not just passively carrying around these cosmic elements. You're actively processing them, using them, transforming them through the miracle of biological chemistry. Every thought you have, every decision you make, every emotion you feel is mediated by atomic interactions involving elements that were forged in neutron star environments. Think about what this means. When you're having a conversation with someone you love, the neural processes that create your thoughts and emotions are directly utilizing atoms that were created in some of the most extreme physics laboratories in the universe. You are cosmic matter that has become conscious of its cosmic origins. And here's the detail that will give you chills. The precision timing that neutron stars maintain, more accurate than any human-made clock, provides a cosmic perspective on the nature of time itself. Pulsars keep time so precisely that astronomers use them as cosmic clocks to detect gravitational waves and navigate spacecraft through the solar system. This incredible precision suggests that the universe itself operates according to principles of timing and causality that are far more exact than anything we experience in daily life. But what does this mean for how you experience time? Every second you live, every moment of consciousness you experience is part of a cosmic timing system that connects you to the most precise mechanisms in the known universe. When you're feeling rushed, stressed about deadlines, or anxious about the future, remember this. You exist within a cosmic timing framework maintained by neutron stars spinning with precision that exceeds human comprehension. The universe itself operates on timescales that range from the microsecond precision of pulsar rotations to the billion-year cycles of galactic evolution. Your personal timeline, your birth, your experiences, your eventual death, is part of this vast cosmic chronology. Understanding this doesn't make your individual moments less meaningful. Instead, it reveals that your personal experience of time is connected to the fundamental rhythms of the universe itself. Now let's talk about something even more profound. What neutron star physics reveals about the nature of your own consciousness. The holographic principle that might govern neutron star information storage suggests that reality itself might be more layered, more information-based than your direct experience indicates. If consciousness operates on similar holographic principles, and some neuroscientists think it might, then your sense of self isn't just a biological phenomenon. It's part of a cosmic information processing system that connects you to the fundamental structure of reality. Here's what this means practically. When you make a decision, when you solve a problem, when you create something new, you're not just using your individual brain. You're participating in information processing patterns that might be fundamental to how the universe itself organizes and maintains complexity. The same principles that allow neutron stars to preserve vast amounts of quantum information in incredibly dense configurations might be operating in your brain right now, allowing you to maintain memories, process complex thoughts, and maintain a coherent sense of identity over time. But let's bring this to an even more personal level. What does it mean to love someone, knowing what we know about neutron stars? When you feel love for another person, you're experiencing an emotional state that emerges from neural processes involving atoms created in neutron star environments. But more than that, if consciousness has holographic properties similar to those proposed for neutron stars, then your love might literally create information patterns that persist beyond the immediate biological processes that generate them. The deep emotional connections you form with other people might be creating quantum information structures that like the information encoded in neutron stars, cannot be destroyed but only transformed. Think about how this changes your understanding of relationships. Every meaningful connection you make with another person might be creating persistent information patterns in the quantum structure of the universe. Your love, your friendships, your family bonds might not be temporary biological phenomena, but permanent additions to the cosmic information content of reality. And here's the practical implication. If your thoughts, emotions, and relationships create persistent information patterns, then every moment of consciousness you experience has cosmic significance. Every kind act, every moment of understanding, every instance of compassion doesn't just affect the immediate present. It becomes part of the permanent information structure of the universe. This perspective doesn't make you responsible for cosmic outcomes beyond your control. Instead, it reveals that your individual choices and experiences are part of something much larger and more enduring than you might have imagined. Now, let's talk about death, the ultimate personal reality that neutron star physics illuminates in unexpected ways. Neutron stars are stellar corpses, the collapsed cores of dead massive stars, but they're not truly dead. They're incredibly active, emitting energy, processing information, maintaining complex magnetic fields, and participating in cosmic processes that will continue for trillions of years. What does this tell us about the nature of death and persistence? If matter and information can be transformed, but not destroyed, as demonstrated by neutron star physics, then death might not be an ending, but a transformation. The atoms in your body will eventually be recycled through biological processes, geological cycles, and ultimately, cosmic processes. Some of those atoms might eventually find their way into future stars, planets, and perhaps even future living beings. In this sense, you are part of a continuous cosmic recycling system that connects you to both the deep past and the far future. But if consciousness really does create persistent information patterns, then something essential about your experience of being conscious might also persist in some form, encoded in the quantum information structure of the universe itself. This doesn't necessarily mean personal immortality in any conventional sense. Instead, it suggests that your consciousness contributes something permanent to the information content of reality, something that, like the information encoded in neutron stars, cannot be destroyed but only transformed. Here's how this changes your daily experience. Every moment of awareness, every instance of consciousness, every experience of beauty, love, or understanding becomes an irreversible contribution to the universe's information content. You're not just experiencing reality, you're actively creating it. When you're walking outside and suddenly struck by the beauty of a sunset, you're not just having a personal aesthetic experience. You're creating new information patterns in the universe, quantum states that represent that unique moment of consciousness experiencing beauty. When you solve a problem creatively, you're not just finding a solution. You're adding new organizational patterns to the cosmic information structure that might influence how future complexity emerges in the universe. When you show compassion to another person, you're not just affecting their immediate emotional state. You're creating information patterns that represent conscious beings choosing cooperation and care over indifference and harm. But here's the practical question. How do you live differently, knowing what you now know about neutron stars and your cosmic connections? First, recognize that you are not separate from the universe. You are the universe becoming conscious of itself. When you look up at the night sky and contemplate neutron stars, you're engaging in a form of cosmic self-reflection. The atoms in your brain that process those thoughts were created in the same processes that created neutron stars. Second, understand that your individual life has cosmic significance, not because of its scale, but because of its information content. Every conscious experience you have adds something irreducible to the universe's complexity. Third, appreciate the precision and elegance of cosmic processes while recognizing your place within them. The same physical laws that govern neutron star behavior also govern the chemical processes in your brain. You exist within a universe of extraordinary precision and beauty, and you're capable of recognizing and appreciating that precision and beauty. Fourth, cultivate a sense of temporal perspective that connects your daily experience to cosmic timescales. When you're dealing with immediate problems or stresses, remember that you exist within cosmic cycles that operate on timescales from microseconds to billions of years. This doesn't diminish the importance of your immediate concerns, but it provides context that can reduce anxiety and increase resilience. Finally, recognize that consciousness itself might be one of the most extraordinary phenomena in the universe, as remarkable in its own way as neutron stars or black holes. The fact that you can think about neutron stars, understand their physics, and contemplate your connection to them represents a cosmic achievement that's still unique, as far as we know in the observable universe. What we're about to explore next will show you that this cosmic perspective on consciousness and connection has profound implications for how humanity as a whole might navigate its future in a universe filled with both incredible beauty and unimaginable dangers. Here's a question that will determine the future of human civilization. What happens when we develop technology advanced enough to directly study neutron star material, harness neutron star energy, or even visit these cosmic extremes in person? We're standing at the threshold of a new era in neutron star science, where theoretical physics meets practical technology in ways that could transform not just our understanding of the universe, but our capabilities as a technological civilization. But first, let me blow your mind with what we're already accomplishing with current technology. The detection of gravitational waves has opened an entirely new field of astronomy that's advancing at breathtaking speed. Since the first detection in 2015, we've observed dozens of gravitational wave events, and each one teaches us something new about neutron stars, black holes, and the fundamental nature of spacetime. But here's what's coming next that will revolutionize our understanding: space-based gravitational wave detectors. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will be able to detect gravitational waves with frequencies that ground-based detectors cannot observe. LISA will consist of 3 spacecraft forming a triangle with sides 2.5 million kilometers long, nearly 7 times the distance from Earth to the Moon. Think about what this means. We're going to build a gravitational wave detector larger than anything that has ever existed, capable of detecting space-time distortions from neutron star mergers, occurring billions of light years away with precision that approaches the theoretical limits of measurement. But LISA will do more than just detect distant neutron star collisions. It will be able to observe the in-spiral phase of neutron star mergers, the months or years of orbital decay that lead up to the final collision. This will give us unprecedented insight into neutron star structure, behavior, and the exotic physics of matter under extreme conditions. Here's what will blow your mind about future neutron star observations. We're developing techniques to study neutron star interiors, using artificial intelligence and machine learning algorithms that can analyze gravitational wave data in ways that reveal the equation of state of nuclear matter. The equation of state describes how matter behaves under different conditions of density, pressure, and temperature. For neutron stars, this equation of state operates in regimes that we cannot reproduce in any terrestrial laboratory. But by studying gravitational waves from neutron star mergers, we can essentially use these cosmic catastrophes as physics experiments that reveal the fundamental properties of matter. The scientist leading much of this work is Bangalore Sathya Prakash, a theoretical physicist who has developed computational methods for extracting maximum information from gravitational wave signals. His techniques allow us to determine neutron star masses, radii, and internal structure from gravitational wave data with precision that seemed impossible just a decade ago. But here's where the future becomes truly mind-bending. Some researchers are working on proposals for direct neutron star exploration. Obviously, we cannot visit neutron stars with current technology. The gravitational fields, magnetic fields, and radiation environment would destroy any conceivable spacecraft long before it reached the surface. But we can imagine technologies that might someday allow us to study neutron stars more directly. Advanced space telescopes operating in the far future might be able to resolve the surfaces of nearby neutron stars, potentially revealing details about their crystalline structure, their magnetic field configurations, and their spin dynamics. Even more speculative are proposals for stellar engineering, technologies that might allow advanced civilizations to manipulate neutron stars for energy production or other purposes. Consider this possibility. A sufficiently advanced civilization might be able to extract energy from a neutron star's rotation by using its magnetic field as a cosmic generator. The energy available from a single rapidly spinning neutron star could power an entire galactic civilization for millions of years. But here's the detail that will keep you up at night. If such technologies are possible, then some civilizations in the universe might already be using them. This raises the possibility that some of the neutron star signals we detect might actually be artificial, the signatures of cosmic engineering projects operating on scales that dwarf anything we can imagine. The physicist Freeman Dyson famously proposed that advanced civilizations might build structures around stars to capture their energy output. Similar Dyson spheres around neutron stars could capture the enormous energy output of these objects while providing a platform for civilization-scale engineering projects. If such structures exist, they might be detectable through their effects on neutron star emission patterns. Some researchers are already looking for artificial signatures in pulsar data, periodic variations or patterns that might indicate technological manipulation of neutron star properties. But let's bring this back to more immediate implications for human civilization. The study of neutron stars is driving the development of technologies that have applications far beyond astrophysics. The computational methods developed for analyzing gravitational wave data are being adapted for medical imaging, financial modeling, and artificial intelligence applications. The precision timing techniques developed for pulsar studies are being used to improve GPS accuracy, telecommunications synchronization, and quantum computing applications. Most importantly, neutron star research is pushing the boundaries of our understanding of fundamental physics in ways that could lead to revolutionary technological breakthroughs. Here's what will blow your mind. Some theoretical physicists believe that understanding neutron star physics could provide insights into the development of room temperature superconductors, exotic forms of matter that could revolutionize energy storage and transmission, and even theoretical technologies like faster-than-light communication. The exotic matter that exists in neutron star cores, if we could understand and potentially reproduce it, might have properties that seem like magic from our current technological perspective. But perhaps the most profound implication of neutron star science for human destiny is what it reveals about the cosmic context of our existence. Neutron stars demonstrate that the universe is capable of creating and maintaining structures of incredible complexity and precision under the most extreme conditions imaginable. They show us that matter, energy, space, and time can be organized in ways that push the limits of what's physically possible. This suggests that the universe itself is far more creative, far more capable of generating unexpected phenomena than we typically imagine. If the universe can create neutron stars, objects that maintain atomic clock precision while spinning hundreds of times per second in magnetic fields trillions of times stronger than anything on Earth, then what else might be possible? Could the universe create forms of matter, energy, or even consciousness that we haven't yet imagined? Could there be natural phenomena operating on scales or in dimensions that we haven't yet detected? The study of neutron stars teaches us humility about the limits of our current understanding, while simultaneously inspiring us to push those limits as far as possible. But here's the question that will define humanity's cosmic future. As we develop increasingly sophisticated technologies for studying and potentially manipulating extreme cosmic phenomena, how do we ensure that these capabilities are used wisely? Neutron stars remind us that the universe contains forces and energies that could easily destroy not just human civilization, but entire planetary systems. As we develop technologies that operate on cosmic scales, we need frameworks for thinking about cosmic ethics, cosmic responsibility, and the long-term consequences of our actions in a universe filled with both incredible opportunities and unimaginable dangers. What we're about to explore in our final section will bring together everything we've learned about neutron stars to reveal the deepest truth about your place in this cosmic story and why understanding these extreme objects might be essential for humanity's survival and flourishing in the universe. We've reached the moment where everything comes together, where all the mind-bending physics, all the cosmic catastrophes, all the exotic matter and warped spacetime converges on a single, transformative truth about who you are and why your existence matters in this universe. Here's the ultimate revelation that will forever change how you see yourself. You are not just made of neutron star material. You are a neutron star process. You are nuclear fusion and information processing and gravitational organization operating at biological scales. You are the universe's way of experiencing itself, understanding itself, and ultimately transcending its own limitations. Let me show you exactly what I mean, and prepare to have your understanding of existence completely revolutionized. Every atom in your body was forged in stellar cores operating under conditions similar to those found in neutron stars. The nuclear processes that created the carbon, nitrogen, oxygen, and other elements essential for life require temperatures, pressures, and densities that approach neutron star conditions. But here's what makes you extraordinary. You've taken those atoms, forged in cosmic extremes, and organized them into patterns of incredible complexity and beauty. Your DNA contains information storage capabilities that rival anything found in neutron star matter. Your brain processes information with efficiency and creativity that might exceed even the most sophisticated astrophysical phenomena. Think about what this means. The same universe that creates neutron stars, objects so extreme they challenge the boundaries of known physics, has also created you. And you possess something that, as far as we know, neutron stars don't have: consciousness, creativity, and the ability to understand and appreciate the cosmos that created you. You are quite literally cosmic matter that has become conscious of its cosmic origins. When you contemplate neutron stars, you are engaging in a form of cosmic self-reflection. The universe is using your consciousness to understand its own most extreme creations. But the significance goes deeper than just cosmic self-awareness. Throughout this journey, we've seen how neutron stars operate as cosmic precision instruments, maintaining timing accuracy that exceeds human technology, preserving information under the most extreme conditions, and participating in processes that create the very elements essential for life. You embody all of these same principles, but at biological scales and in ways that might be even more remarkable. Your consciousness maintains continuity of identity and memory with precision that rivals pulsar timing. Despite the fact that most of the atoms in your body are replaced every 7 years, you maintain a coherent sense of self that persists across decades. Your brain processes and stores information with density and efficiency that might approach or even exceed what's possible in neutron star matter. The human brain contains roughly 86 billion neurons, each connected to thousands of others, creating a network with more connections than there are stars in the observable universe. Most importantly, you participate in creative processes, generating new ideas, solving problems, creating art and music and literature that add genuinely new information content to the universe. You're not just processing existing information, you're creating new patterns, new possibilities, new forms of beauty and understanding that didn't exist before your consciousness engaged with them. Here's what will blow your mind. In some ways, you might be more cosmically significant than neutron stars themselves. Neutron stars are incredibly sophisticated information processing and storage systems. But as far as we know, they don't create genuinely new information. They process, preserve, and transform existing information, but they don't seem capable of the creative leap that consciousness represents. You, on the other hand, can take information about neutron stars, photons that have traveled across space for thousands of years, gravitational waves that have rippled through space-time for billions of years, and transform that information into understanding, appreciation, wonder, and new ideas about what might be possible in this universe. You are participating in what might be the universe's most important evolutionary process, the development of consciousness capable of understanding and ultimately transcending the physical limitations that govern even the most extreme cosmic phenomena. But here's where your cosmic significance becomes truly profound. You are part of a process that might be essential for the universe's own long-term survival and development. The universe is approximately 13.8 billion years old, but it faces a long-term future that includes challenges that might require conscious intervention to overcome. Stars will eventually burn out, protons might eventually decay, and the universe might face what cosmologists call heat death, a state where all useful energy has been dispersed and no further organized processes can occur. But consciousness, the kind of consciousness that you embody, might be the universe's solution to these challenges. Advanced consciousness might eventually develop technologies that can manipulate matter and energy on cosmic scales, potentially allowing the creation of new stars, new sources of energy, and even new forms of organization that could extend the universe's capacity for complexity and beauty, far beyond what's possible through natural processes alone. In this scenario, consciousness isn't just a byproduct of cosmic evolution. It's the goal toward which cosmic evolution has been working for nearly 14 billion years. And you are part of that process. Your consciousness, your creativity, your ability to understand and appreciate the cosmos that created you, makes you a participant in what might be the universe's most important project, the development of intelligence capable of ensuring that beauty, complexity, and conscious experience can persist even in the face of cosmic challenges that would otherwise end all organized processes. But let's bring this back to the practical, personal level. How does knowing this change how you live your life? First, recognize that every moment of consciousness you experience is cosmically precious. You are the universe experiencing itself subjectively, and that subjective experience adds something genuinely new to the total information content of reality. Second, understand that your creative contributions, however small they might seem, are part of a cosmic process of increasing complexity and beauty. When you create something beautiful, solve a problem creatively, or help another conscious being flourish, you're participating in the universe's ongoing project of self-transcendence. Third, appreciate that your ability to understand and appreciate cosmic phenomena, like neutron stars, makes you a cosmic detective, a cosmic explorer, a cosmic artist. You're using consciousness that emerged from cosmic processes to understand and appreciate those same cosmic processes. Fourth, recognize that your relationships with other conscious beings have cosmic significance. When you love someone, when you share understanding, when you work together to create something beautiful or solve important problems, you're participating in the development of collective consciousness that might eventually become capable of cosmic scale, creativity, and problem solving. Finally, understand that your mortality doesn't diminish your cosmic significance. It intensifies it. The fact that your individual consciousness is temporary makes every moment of awareness, every creative contribution, every act of love and understanding more precious, not less. You are made of neutron star material, but you are more than neutron star material. You are the universe that created neutron stars, discovering its own capacity for consciousness, creativity, and transcendence. The same cosmic processes that create neutron stars, nuclear fusion, gravitational collapse, magnetic field generation, precision timing are operating in your body and brain right now, but organized in patterns that enable something that might be unique in the known universe: conscious appreciation of cosmic beauty and complexity. When you look up at the night sky and contemplate the neutron stars scattered throughout the galaxy, you are engaging in what might be the most important activity possible: cosmic matter becoming conscious of its cosmic origins and contemplating its cosmic destiny. You are not separate from the neutron stars you've learned about. You are their conscious expression, their way of understanding themselves, their participation in the universe's ongoing project of self-discovery and self-transcendence. And that makes you not just cosmically connected, but cosmically essential. If this journey through the physics of neutron stars has changed your understanding of your place in the cosmos, then you're ready to join a community of cosmic explorers who recognize that consciousness itself might be the universe's most important experiment. Share this video with someone whose worldview you'd like to expand. Like and subscribe if you want to continue exploring the deep connections between extreme physics and human consciousness. And tell me in the comments, how has learning about neutron stars changed your understanding of your own existence? Because remember, you are made of neutron star material, animated by cosmic processes, and capable of understanding and appreciating the universe that created you. You are not just living in the cosmos. You are the cosmos becoming conscious of itself. And that might be the most important thing happening anywhere in the known universe. As we reach the end of this cosmic journey, I want you to carry with you one final image that captures everything we've explored together. Right now, at this very moment, scattered throughout our galaxy and beyond, neutron stars are spinning with precision that exceeds human timekeeping, generating magnetic fields that could erase hard drives from millions of miles away, and occasionally colliding in explosions that forge the very elements from which you are made. These cosmic monsters, stellar corpses that refuse to die quietly, continue their eternal dance through space and time, creating the conditions that make planets possible, life possible, and consciousness possible. And here you are, made from their ancient alchemy, contemplating their existence with a brain that processes information as sophisticatedly as they do, but with something additional that makes you truly extraordinary: the capacity for wonder, appreciation, and understanding. You are the universe's way of experiencing awe at its own creations. You are cosmic matter that has developed the ability to contemplate cosmic origins. You are the inevitable result of 13.8 billion years of cosmic evolution toward increasing complexity, beauty, and consciousness. The neutron stars that created the atoms in your body continue their cosmic dance, and you, their conscious descendant, continue the dance they began, but now with awareness, creativity, and the capacity to ensure that the universe's experiment with consciousness continues into the far future. You are made of neutron stars, but you are more than neutron stars. You are their conscious legacy, their gift to the cosmos, their contribution to the universe's ongoing project of understanding itself. And in understanding them, you understand yourself. In appreciating them, you appreciate the cosmic processes that made your existence possible. In being amazed by them, you participate in what might be the most important activity in the universe: conscious matter experiencing wonder at the reality that created it. The universe created neutron stars to forge the elements essential for planets and life. But it created you to understand neutron stars, to appreciate them, and to carry forward the cosmic story they began. Welcome to your cosmic inheritance. Welcome to your role in the universe's greatest experiment. Welcome to the ongoing adventure of consciousness, exploring the reality that made consciousness possible. The neutron stars are still out there, spinning, pulsing, occasionally colliding, continuing their ancient cosmic work. And you are here, conscious and aware, carrying forward their legacy in ways they never could. This is who you are. This is why you matter. This is your place in the cosmic story. And the story is just beginning.